Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we'll be looking at GCSE Physics, the National Grid. We're gonna take a break from the hardcore electricity stuff, and I thought today we're gonna do a bit more relaxing lesson on the National Grid. It's an interesting topic because National Grid is one of the very important inventions that's often looked over. You know, when we think about inventions that changed the world, we think about internet, we think about things like wheel, evolution perhaps, but National Grid is actually very important, one of the very important inventions to do with electricity, and it has changed our world. So I believe this is something that's a good thing to learn, I suppose. So, without further ado, let's get started. First of all, what is a national grid? Now, national grid is a way to distribute electricity across the entire country. And it's a way to distribute electricity no matter where the power stations are and where the consumers are. You can have a power station at one end of a country, and you can use national grid to deliver electricity from that power station all the way to some house at the end of it, at the other end of country. You can do that very easily using the national grid. It's a system that connects all the sort of power station in the country, and it connects them to all the consumers, all the houses, all the offices, businesses. It's essentially a grid that delivers electricity to the entire country. Now, so it works something like this. So here I drew it out like this. So in blue we have power stations, in red we have houses. So for example, we can have two power stations. Now, if we didn't have national grid, we would have two power stations here along with these two houses. And those power stations could deliver electricity directly to those houses. They could, absolutely. But that would be a bit of a waste. You have two massive power stations that are powering only two houses. Whereas on the other end, you have a village that is full of houses. You have quite a few people living there using electricity. However, those power stations are not there. So without national grid, they could not deliver electricity. So these guys would be left without any form of electricity. So national grid essentially connects power stations to the houses, or businesses, offices, whatever, and that allows them to deliver electricity all the way. It's essentially a network of cables. These cables deliver electricity to these houses as needed. Now that's another important point about national grid, because the demand for electricity changes throughout the day, throughout the seasons. In winter, for example, demand for electricity would increase because people are heating their houses, often using electric heaters, and it's colder. And also throughout the day, you would get differences because in the morning, people start cooking up their breakfast and maybe catching up on some TV just before they leave to work or school. So the electricity demand will shoot up. During midday, you will get less because most people are at work. And then after people come back from work, they want to relax, they want to watch their TV, whatever. And they most likely will be using electricity at that point. So in afternoon, electricity demand will go up. Also at night, it's colder, so people may switch on heating and things like that. So electricity demand varies throughout the day. And say if we had a small power station in a city, then maybe when the electricity demand goes up, that power station would not be able to supply that electricity because it's too small, and obviously it can't produce enough electricity to provide for everybody that needs it at this given moment. And that's where national grid comes in, because then a bigger power station can step in because it's connected and can pick up the slack and can meet the demand. Usually the bigger power stations actually, normally they won't run at the maximal capacity because of national grid. They're planned out in such a way that they will rarely run at the maximal capacity, and so they have plenty of wiggle room to accommodate for the increases in demand and prevent power cuts and things like that. So that's very important. So that's a top-down view of how National Grid works. You have a power station connected to the cable, which connects it to the house, boom, electricity delivered. However, the reality is slightly more complex. It is largely the concept, but there are a few more components that we need to go over now. So here I drew out more detailed graph of how National Grid works. Now, so here we have a power station. That's where we start off. Power station is connected to National Grid because power station generates that electricity. Power station generates that electric power, which will be supplied across the country. Now, before the electricity generated in power station hits the cable, the grid, it needs to go through a step-up transformer. What is a step-up transformer? Now, before I go over that, let's see. Because essentially what we are doing is when we are delivering electricity, we are delivering electric power. And that's important. Here we have an equation. P stands for power. Power is equal to voltage times current. That's the equation for power. One of the equations for power. We will come across it later on, so if you forget, we will be coming across it in other videos when we go back to the more hardcore electricity stuff. So knowing that equation, we need to deliver huge amounts of power. If we want to supply electricity to the entire country, we need to deliver huge, immense amounts of power. So how do we do this? Well, the equation tells us that to deliver large amounts of power, we either need very high voltage or we need very high current, or combination of both, high voltage and high current. Now, if we went with high current, if we decided that we are going to deliver power by ramping up the current, there would be a problem, because when current is high, things tend to heat up. So it's more wasteful, because if a cable heats up, what that means is that this cable is releasing thermal energy. So along the way, we are losing that power. The work done is less efficient. So that's not the best solution. The best solution is to ramp up the voltage, to make the voltage incredibly high, and that way we can keep the current very low, and that way we are delivering massive amounts of power whilst keeping the current low, so the cables do not heat up actually. So that's a much more efficient way of transporting that sort of electric power. And that's where step-up transformer comes in. Step-up transformer is a building, usually, which basically increases the voltage. It's a coil through which we are going to increase the voltage. You don't need to know at this stage, you don't need to know exactly what happens in a transformer, so we won't get into that too much. So essentially, transformer ramps up the voltage all the way up to 400,000 volts from whatever power station supplies, whatever voltage power station supplies, doesn't matter. Step-up transformer will step it up to 400,000 volts. That's what the currently National Grid uses to transport the voltage that National Grid uses. So basically every point at which we have a step-up transformer, it will step up the voltage to 400,000 volts. And that way we standardize everything. We keep everything the same across the grid. That's the voltage we use. So that, I remind you again, makes it so we are transferring large amounts of power whilst keeping the current low to prevent heating up of the cables. However, when we want to supply it to consumers, appliances will not be able to handle such an insane voltage. You know, everything will just sort of explode and break. And also, that is just incredibly dangerous. That is just incredibly dangerous. So, what we need to do now is we need to decrease the voltage. So, essentially, we use a step-down transformer. And step-down transformer will decrease the voltage from 400,000 to eventually, by the time it reaches the consumer, it will be 240 volts. And that in UK, in various other countries, it varies. In European Union, is slightly different, so it may vary between the countries. But in UK, we are getting it down from 400,000 volts to 240 volts by the time we reach the consumer, and that allows much safer use of that power. It's much safer, and obviously electric appliances can handle that power. So that's why we use these transformers. That's why we use the step-up transformer, and that's why we use the step-down transformer. So that's essentially how National Grid works. So this is it for today, guys. Thank you very much for watching my videos. I really appreciate when you guys watch my videos. If you want to stay up to date on daily math, science, and some biomedical science videos, don't be shy, hit that subscribe button below. If you think that video helped you, and I hope that video helped you, give me a thumbs up. Thank you again for watching, and see you next time.